Okay, this is a quick video about blackbody radiation. When you think about quantum theory, you probably don't think about a red hot poker, but the truth of the matter is quantum theory was invented precisely to explain why a poker glows red hot exactly the way it does when it gets hot. So this is described by something called the blackbody spectrum. And you can think of the graph on the right as experimental. Basically, people looked at different wavelengths at different temperatures to see what the spectrum looked like. And the story of this video is how people figured out how to fit an equation to it. Okay, so just a few things to point out is that every object emits radiation at every wavelength all the time. The truth of the matter is, though, humans are rather short-sighted. We can only see a very small portion of the wavelengths, and depending upon the temperature, there may not be enough height here in order for us to see it. So this height is the intensity. It's how much power you're seeing at each wavelength. And so notice a couple things happen. As the temperature increases, the curve gets higher, meaning overall there's more light put out. But not only that, not only does that happen if we take a closer look, but you can also see that as it gets hotter, the peak of the curve shifts to the left. In other words, at 4,000 degrees, the wavelength that puts out the most is in the red, and the wavelength that gets put out the most at 5,500 degrees is blue. Now, to be clear, this does not mean that at 5,500 degrees things look blue. In fact, the sun is about 5,500 degrees, and the sun is white. Okay, it's yellow on Earth, but in space, it's white. And so what happens is, by the time you get to 5,500 degrees, yes, there's more blue than anything else, but there's also so much of every color that your brain can't make heads or tails of what's going on, and so it just says, hey, this is white. I don't know what to do with it. A couple laws that you may have seen from thermodynamics. The first one is called Stefan's law, sometimes it's called Stefan-Boltzmann law, but basically it says that the intensity, in other words, the overall size of this thing increases like t to the fourth. So if you increase the temperature a little bit, it gets a lot brighter. The other one is that the peak wavelength, this is called Wien's displacement law, depends on temperature. If you increase the temperature, the wavelength gets smaller, and you can see that with these curves. Okay, so how do we fit a model to these curves? There were two big thrusts made at this. One was by these two guys, Rayleigh-Jeans, and to be fair, they did most of the work here. What Planck did was he fixed their curve. So why did their curve need to be fixed? You may have heard of something called the ultraviolet catastrophe. Well, Rayleigh and Jeans used the laws of classical electricity and magnetism and thermodynamics to derive this law, and we'll do that. I'll show you how to do it. But if you look at the denominator, there's a 1 over lambda to the fourth. And what does 1 over lambda to the fourth look like? It goes to infinity. It never comes down. And so Rayleigh-Jeans basically found out that according to classical theory, there's an infinite amount of light coming from everything. And that just is not true. So what did Planck do? Planck figured out a way to force the curve to come back down by adding this factor here. Now, the way he added this factor is how this came to be known as quantum theory. And I just want you to keep in mind a couple of things. That I'm going to tell you how he did it, and you probably are not going to like it. He didn't really justify why he did it, but what I'm going to tell you is that it works. So if you take Planck's intensity as a function of lambda and you integrate it over all wavelengths, guess what? You get the Stefan-Boltzmann law. You even get the correct constant. If you take a derivative of Planck's function and you find the peak wavelength, well, you'll find that that matches Wien's displacement law. So like it or not, Planck's theory is totally consistent with experiment. Okay, so let's see what they did. So right now I have things written in terms of the intensity, which is what we're measuring with our devices, but the truth is it's easier to make pictures and do calculations with energy rather than intensity, so I want to do a little conversion. So the intensity depends on the energy density. What you've probably seen before is something that looks like I equals C times U, but that is in the textbook. Typically they'll say, you know, hey, there's a bunch of light and it's all moving one direction and it pierces this surface pi r squared, and so the intensity depends on that. That's not what we're doing. What we're doing is we have a source that's hot and it's spitting out radiation in all directions. And so what does that mean? That means it gets spread over a sphere that has surface area 4 pi r squared. There's your factor of 4. In other words, that's kind of a hand-wavy argument to explain why that 4 is there. We won't dwell on it too long, except to say that it changes some of the constants out front. Okay, so now we've recast in terms of energy density, and I just want to explain really what I mean by energy density. Energy density means that if you integrate all the energy density over lambda, you get the total energy. That's the same thing as saying find the energy of each oscillator. I'll explain by what I mean by that in a minute, and then find out how many oscillators have that energy, and then add up all those oscillators. That's what that integral means. And so we've got two things we need to figure out. One is the average energy for a particular oscillator at a particular wavelength, and the other is how many oscillators there are in some given wavelength region. So I've kind of written that down here. In other words, E is the average energy of each oscillator, and n of lambda is the number of oscillators between lambda and lambda plus d lambda per unit volume. So we'll have to keep that in mind. What do I mean by energy? Well, look, just remember, what is the source of light? It's electrons jiggling back and forth like they're on springs. And so when I say energy, what I mean is these electrons can jiggle with a big amplitude, they can jiggle with a small amplitude, they can jiggle with whatever amplitude they want, and that in some sense informs their energy. What's the wavelength? Well, they can jiggle with whatever frequency they want, and then that will inform different frequencies of light as well. Okay, so just to put both these laws above in terms of these two concepts we have, so this part of the law is n of lambda d lambda. N of lambda d lambda. And notice Planck and Rayleigh-Jeans actually agree. What they disagree about is what the average energy is. So the average energy for Rayleigh-Jeans, I'll show you how to do this in just a second. They came up with KT, and Planck comes up with something, well, let's just say more complicated. I'll show you how they do both, and I think we'll start there. I will also show you how to find this. This is called the number density or the density of states, but it's a little longer, and I'm just going to tack it on at the end. So let's start where they disagree, and this is really the punchline anyway. Okay, so if we look at the energy and we want to focus on how did they get these numbers for the energy. Okay, so Rayleigh-Jeans, the first thing they did was they said, okay, the number of oscillators, so the number of photons that have a particular energy E is proportional to this factor. This is called the Boltzmann factor, and if you've seen it before, you're like, oh yeah, sure, that makes sense. If you haven't seen it before, I bet you have seen it before. If you've ever seen the Maxwell speed distribution, so that looks like v squared e to the minus mv squared over 2kt. Or if you've ever done the density of air as you go up, that looks like density at the ground times e to the minus mgh over kt. In other words, as the density decreases, what we're saying is it's less probable to find something there. But look, this is a potential energy. Look, this is a kinetic energy. The idea that the probability of having a certain velocity and the probability of some density, right, they all depend on the energy. And so if you want to know more about the Boltzmann factor, you can go and look it up. I don't want to spend more time on it in this video. Perhaps I'll make another video about just that sometime, but we'll have to accept that for now. Again, what do I mean by energy? It's these little oscillators. They can have whatever energy they want, according to Rayleigh-Jeans. And if I want to find the average energy, basically what I do is I say, well, what are all the possible energies? Okay, what's the probability of having each of those energies, or what fraction have that energy? So I take the number that have that energy times the energy, and then I divide by the total number. So this is total energy on top, total E, over total N on the bottom. In other words, the number that have it times the energy of each one, add them all up, okay, and that's obviously that. I guarantee if you do those integrals, you'll get KT. They're not particularly interesting. Plug them into an online calculator if you like. Okay. This, again, is no good because you could see here the density of states. As I get smaller wavelength, I have an infinite number of wavelengths. If they all have an energy KT, guess what? I'm going to have an infinite amount of energy. So what did Planck do different? Okay, Planck starts from the exact same place. He says, nope, Boltzmann good. That doesn't need to be changed. This is what Planck says that's different. Planck says E is not allowed to have any value. E can only have integer multiples of some fundamental value. Now, why does he do that? Because he knows what the final result wants to look like. He's seen these experimental distributions, and he knows that he needs to come up with something to crush this UV catastrophe. And this is the term that crushes it. He also is really good at math, and he happens to know that if he does a sum will produce something that looks like that. So this is the idea. He says, I want this fundamental energy to be proportional to frequency. That way, as the energy increases, it'll be much less likely to have particles in that range. So the energy can be whatever it wants to be. You're just not going to find any oscillators that have it, right? And so that means that in terms of lambda, I can just replace F by C over lambda, and the proportionality constant I say is H. Planck didn't call it H. I don't know what he called it, and he certainly didn't call it Planck's constant, but we do today because, again, this works. So here's your energy, and again, I'm going to do the same thing I did with Rayleigh-Jeans, only now notice the integral becomes a sum. The sums are admittedly a little bit more difficult to see than the integrals, but actually they're really not that bad. This guy, geometric sequence. This guy, almost a geometric sequence. There's a neat little derivative trick that you can do in order to figure it out. There's a million places that do it. I'll let you look at one of those to see. But this is the punchline. The top looks like this. The bottom looks like this. And if you do a little bit of algebra, ta-da! This is what Planck did. And this is what we mean when we say he invented quantum mechanics. What's quantum about it? It is discrete. You are doing a sum. You are only allowed to use certain values of energy. If you stopped watching the video right here, I think your life would be richer for it. I promised I am going to derive this next. Let me just say one thing about this really quickly, that you may not like this. Planck had really no explanation for why he did this other than it works, but I will tell you, it works great. It really does produce that spectrum that we're looking at on the left. Okay, so what's next? Now what we want to do is derive this guy. So it takes a little bit to do, but it's worth doing because the way that you derive this number density or density of states, you end up doing in a lot of other places in physics. And so this is the first time you'll see it, but it's definitely not the last time you'll see it. So what we're trying to find is the number of oscillators that occur in some range of wavelengths. And so let's set the stage. What is our black body? It's a box. And it's a cube that has all the same sides because it's easy, right? If you want to do something that's less easy, you go ahead. I'm doing the easy version. And if it makes you feel better, look, you can always build a more complicated object out of simple objects. That's the whole point of calculus, right? Okay, so the idea is there's light that shines on this that keeps it in equilibrium. All of that light is absorbed. None of it is reflected. That means that inside the box, it's a hollow box, there's a bunch of light bouncing around and accidentally sometimes it escapes. Some of the light is red, some of it is green, some of it is purple, but if you're looking over here, all you see is the light that the box produces because there's nothing being reflected. That's what we mean by black body. Okay, so what does the light inside the box look like? Well, one thing to think about is at the sides of the box, the electric field has to be zero. Why does the electric field have to be zero? Because if the electric field were not zero, these oscillators, these electrons, they'd move and they'd rearrange themselves until it was zero. In other words, the electrons would slosh around, and in the process of sloshing around, they'd find some happy intermediate state where the electric field is zero. So if the electric field has to be zero, this actually puts us in a place where we make standing waves, the same ways you did when you looked at waves on a string. We're just doing them with light waves now, right? So what does that look like? There are certain wavelengths that are allowed. These are the wavelengths that fit into this box that has length L. And I drew the first few there, right? What I want to do, though, instead of looking at wavelength, I want to look at something called wave number. It's not a big deal. It's just the inverse of wavelength, more or less. And in one dimension, it really doesn't make that big a difference. But in 3 dimensions, the wave vector actually has a real physical significance and helps us understand this. So that's why I want to switch now. It also makes easier pictures to draw and explain this idea with. So what do I mean? There are some k sub n's. If n is 1, I have one value of k. If n is 2, I have another, and so on. What I want to know is how many different values of k are there within a range of k? I know that sounds really weird, and in one dimension, this doesn't make a lot of sense. I'm just trying to help you understand what I'm trying to do when we get to 3 dimensions. In other words, in this range, I look and I see there are 4 oscillators. If I made the range larger, I'd see 5 or 6 oscillators. I think what we can say, though, is that the number of oscillators I see in this case depends only on how big I make delta k. It doesn't depend on k. It will in 3 dimensions, but we'll get to that when we get to that. So what we want to know when we say n of k dk, what we're really saying is dn dk, oops, typo, dn dk dk, right? That's dn, okay? And so what does that mean? That means I take a derivative and I end up with this, and then here's this thing dk. Now the only thing we have to keep in mind is that there are actually, for each one of these waves I drew, there are actually 2 waves. Because if the direction of propagation is this way, well, I can have oscillation up, down. That's what I drew. What I didn't draw was I can also have oscillation into and out of the page. So what I need to do is actually multiply this by 2. Now the thing, everything except for the dk, that's my n of lambda. So if I just combine this all in one place, I have n is 4L over pi c. And one thing I'll point out, notice I have this tilde here. I've been writing tilde the whole time because ultimately what we want is the number density, or the number per unit volume. And in one dimension, there's no volume, but there is a length. And so what I want to do is make sure I divide by length at the end. And so the idea is this. This is the number of oscillators that have a that are within a range of dk, say, okay? And it's just some boring number. That's the number I want to get when I switch to 3 dimensions. So here we are, 3 dimensions. What happens now? Well, now I have 3 different dimensions to go in. I have a lambda x, I have a lambda y, I have a lambda z. I let the length be L in all 3 cases, just to make life simple. It doesn't have to be. You can redo it without that being the case. So again, we're going to switch to wave, but in this case, the wave number is a vector. So sometimes when you write electromagnetic waves, what you actually write is k vector dot x minus omega t. And so this vector has all the information about lambda x, lambda y, and lambda z in it. What do I mean by that? I mean that the actual wave is moving in 3 dimensions. It's not constrained to move along the axis, and that this is the wave vector along the direction of propagation. The magnitude of the wave vector is the distance between these maxima and minima, and all of this information is contained in there. Okay? So I just want to draw another grid like I did last time. So I set this up. This is just 3 copies of the grid I showed in 1 dimension. Now the thing here is, here I'm taking, say, like, this is only along the x direction. So I'm saying like ny equal nz equals 0. And then likewise, this is the other 2, 0. But the truth is I can mix and match however I want. I could have 1, 3, 7, for example. If I were to fill this out, I end up with a mess. It's a pigsty. Those are all of the states that I'm interested in. But the truth is, I'm not interested in all the states. I'm interested in all the states within a narrow band of wave number. So what does that mean? Well, if I look at the magnitude of the wave number, remember, that's this. Well, all I have to do is just take the magnitude of that vector. And if I crunch those numbers together, okay, now I've got something that depends on Rn. In other words, I'm calling this Rn. In other words, there's some radius involved. What do I mean by that? Let me show you. In other words, these are all the points that I can draw that have a magnitude of k that's all the same. That's that cube I showed you earlier, but now I'm putting a constraint on nx and y and nz, and I'm saying that they all have to have k. If I drew one here and I drew another one right outside that had k plus dk, then what I'm interested in counting when I look for the density of states is how many lattice points there are in this small shell of a region. Now, you might be rolling your eyes and saying, I don't want to count all those balls. You're right. I don't want to count them either. What we can say is that the number of points is approximately equal to the volume. So what does that mean? It's a spherical surface. It's a spherical surface times the thickness, however thick we allow. Now, this 1/8 in front, bear in mind, remember, these are all positive integers. 1, 1, 1. There's no negative numbers. That means I'm constricted to the first octant, and I only want the first eighth of a sphere. So this is the volume of a shell that contains points that go from k to k plus dk. That's how many of them I have, right? And so if I put that up here, I'm just plugging in for what I have below. I end up with something that looks like this. Now notice I still have a tilde here. That tilde is there because I still have L's. So let's put all the L's together. L cubed, that looks like a volume to me. Let's get rid of it. So I get rid of the volume, and this is what I have left. This is n of k dk. This is the number of oscillators that have a k vector between k and dk. And notice now it absolutely does depend on k. So what I want to do is I want to go back and put this in terms of wavelength so that we can match up with the original formula. The k was useful so that we can make our sphere, but now we're done with it. So k is 2 pi over lambda. dk is that. If I substitute, I end up with the thing that I was looking for in the first place. So it's a little weird. If you want, you can go back and you can rewatch it a couple times. You will use this technique again if you do solid state physics and free electron gas and so on and so forth. The point is, we have derived this entire thing more or less from scratch, and we can now say goodbye to Mr. Rayleigh and Mr. Jeans. They did a wonderful job, but their theory is wrong, and Planck's reigns supreme. So this is the final formula we end up with. The key idea is this is discrete differences between energy states. That's what makes it quantum theory. What I'll tell you is that Planck didn't know this, but all systems that have bound states exhibit this property. So atoms, oscillators, all sorts of things. If it is bound, if it's trapped, then you end up with quantization. Around the same time, Planck didn't have much to do with this, but around the same time, people were looking at things called matter waves. In other words, photoelectric effect, photons behave like particles, even though they're waves, and electron diffraction, electrons behaving like waves, even though they are particles. So matter waves and energy quantization are both explained by this guy. And this guy is Erwin Schrödinger, and this is the equation that bears his name. He put quantum mechanics on firm footing and is able to explain all of these effects. Okay, hopefully this video is more helpful than confusing.